if there's no friction, then when the bar makes it down the incline, we talked about the incline yesterday, but the bar makes it down the incline, conservation of energy is how we would express the speed of the bar when it's here. That part's immaterial. The bar just needs something that would have given it velocity so we can go to this next portion of the problem, which is where the problem, I believe, gets interesting. So at this moment, for the time being, I'm going to use just a lowercase v to indicate the velocity of the bar, but it should be made clear that the initial velocity of the bar is the square root of 2gh. So somewhere towards the middle of this problem, if you were actually doing this problem on the exam, you would likely have to do this substitution. So it's something to keep in the back of our mind, but this is just the initial velocity. Our velocity is going to change once we enter this region of space where there is a magnetic field. Now, you have some choices on how you proceed from here. One of the first things you could do is you could just use motional EMF to figure out the direction of the current and the direction of the force on the bar. I'd rather use Faraday's law. I think Faraday's law is a little bit more powerful, but also you might be expected to show Faraday's law under a certain circumstance. They can say, use Faraday's law to derive an expression for the force in the bar, and you would have to use Faraday's law. Everybody got that? So I'm going to start with assigning a variable to this, even though a variable isn't necessary to do what we're going to do. So they don't have to give you the length of the rails. All we need to know if the rails are sufficient for the bar to slide long enough for us to get the data or get the expression we need. So assign something here if you don't have something. I'm just going to go with x for right now. And I'm going to give myself a bit of knowledge of the future that v is going to be equal to minus dx dt. It's minus because it's moving to the right. And if we look, it's making the area smaller. Now, this minus sign isn't going to matter in the long run, but it's important to be considerate of direction in these problems. And since we know later we're going to be taking an integral that's related to the area, and then taking the derivative, which is related to time, knowing that the area that's being that is been created by this bar is getting smaller, is going to be related to that negative sign specifically. Do you follow what I'm saying? We're comparing x with v. And so, and this area is getting smaller. Now, we do need an expression for the flux if we're going to use Faraday's law. And our expression for the flux is still the integral of b dot dA. But I think we can all pretty well agree that this is ornamental, meaning it's nice to have this fancy expression, but the area is just the area of this rectangle, and the magnetic field is constant. There's no dependence of the magnetic field on a particular location of the area. Does that make sense to all of you? We're trying to find ways to increase how quickly you can employ certain rules. So this portion here, you have to ask yourself, is there any dependence of the magnetic field on a particular location of the area? If there isn't, well, then you can probably pull the magnetic field out of your integral. And then ask yourself, is there any dependence on the direction of the area and the direction of the magnetic field? In this indication, the answer is no, there's no dependence there. We know that the area and the magnetic field are perfectly aligned. So you should be able to drop down in one line and say BXL as your flux. There's no reason to make it more complicated. Only if the magnetic field is different in the area in which you're taking the integral do you even have to really be phased by this integral. The only other way that this would come up is if you have a weird area or a weird angle. But if the magnetic field is uniform in that region of space, you can probably jump from the definition of flux right to just taking the magnetic field and multiply by the area. If you're trying to write yourself notes, that's what I'm trying to get at. Again, so if you're trying to be better about this integral will only matter if there's some dependence between location and the magnetic field. Otherwise, B times A, and be done with it. Now, we have to work in a variable that's going to be changing due to the velocity. That's why I'm working in a variable that I created, x, because we need to have that variable. It's related to what's happening here. Now, going on to Faraday's law, because this is just our first step in Faraday's law. Faraday's law is minus n d flux dt. How is the flux changing? Well, the area is changing. We know that. Now, there's only one loop, so n's going to go away. I'm going to leave the negative sign there because the negative sign is a reminder to me that direction is going to be important, and we will need to come up with some information about direction, but we're just going to sub in our flux here. So when I sub in the flux, I'm going to get minus d dt of bxl. Well, the bar doesn't change size, the magnetic field doesn't change its value. The only thing that's changing is x. So this becomes minus bl dx dt, which we've already put in there is minus the velocity. So this is where you get your BLV. Okay. Any question to this point? All right. It's on you. I want you to attempt to use Lenz's law to justify the direction of the current in the bar. So by stating Lenz's law that there is that the flux is being reduced, so the generation of the current is to reinforce the flux that's disappearing, that I think gets you the 2, maybe 3 points for justification for Lenz's law. And then when you're done, indicating that the direction of the current is downwards through the bar. I think that's, make sure if they tell you to do it relative to the bar, do it relative to the bar. Now, the next question I would ask is for you to find an expression for the force on the bar. And this is where this problem gets interesting with the math. So you guys who are my mathletes a bit, this is where I would hope you would perk up. So find an expression for the force on the bar, please. If you don't know where to start, I will start you. That has to be it. But you can't have I in your answer. So you need to get rid of I. Shouldn't be hard. You have a resistor in a single loop circuit. So your very first substitution is likely to use Ohm's law. But you can't have the EMF symbol in your answer. It's got to be based on the physicality of our apparatus. So you'll have to sub in for the EMF BLV. All of this substitution takes place here. Plus the cross product, but I think we can handle the cross product as being 90 degrees. We'll be okay there. So this is the substitution I'm looking for. Any question? Now, you mathy folks, 2 things. Convince yourself the direction of this force is to the left. It has to be. Something's trying to stop the bar from moving. We're not generating a current for free. But also, this has to equal MA. You guys who had in mechanics last year know that this is the first order differential equation. of which you should be able to solve it. I'm going to assume that maybe we need to review that tomorrow.